Hello, in this video I want to try and harness all of the power of my PC to solve a problem. But before we get started, 3 quick points. Number 1, this could be considered quite advanced for this channel, but don't worry, I'm only going to look at some things in light detail. If you are interested in the specific details, the source code is of course available, and we can discuss it on the Discord and in the comments. Point 2, I've no doubt some of the armchair experts out there are going to poke holes all through this. That's okay, because really I'm just taking a very broad look at some of the techniques available to us. And point 3, yes, the lockdown goatee is progressing just fine, thank you very much. So let's get started. All programmers at some point during their programming careers encounter a problem where they really wish they had more CPU power to solve a particular problem. And I'm going to demonstrate this by rendering this Mandelbrot fractal. Now, if you're not an expert on fractal geometry, and I am certainly not an expert on fractal geometry, don't worry. What it really means is we're going to be creating some really cool imagery, and we're going to go and explore them with this tool that I've created in the Pixel game engine. And the idea of a fractal is it's got lots of self-repetition, and those self-repetitions can go on and on and on and on and on, and you can just keep on zooming in on particular locations. And this tool allows you to sort of explore things as if it was a Google map of the Mandelbrot fractal. So as I keep zooming in, I need to perform more and more calculations, and we'll look at the basic calculations of the Mandelbrot fractal in a minute. And we can keep zooming in until we actually run out of precision on my computer, and I'm going to be using 64-bit floating point double types. And I think we're approaching that point now. Yes, there we go. See, things start to get a bit wavy and wobbly, then pixelated, and ultimately completely collapse. She'll just zoom back out. And the nice thing is it zooms to the cursor, so we can really go and explore these patterns and see what's going on. I'm also quite aware that this is exactly the type of video that YouTube doesn't like to show. Because there's lots of noisy pixels going on, it can't compress it very well, and it will require more bandwidth, and during this period of lockdown, bandwidth is at a premium, so apologies in advance if it does look a little bit blurry. However, I'll upload the binary alongside the source code so you can run it on Windows at least. Let's go and have a look here. Lots of detail going on in this particular section. And the tool is quite an interesting tool because we can actually choose the amount of detail we want things to render to. And by increasing this level of detail, we require more and more computations. And so what I want to do in this video is compare various different approaches to solving this rendering problem. And I hope to take you on a journey from simple levels of computation to extreme levels of parallelism. Now, of course, if we're doing a video that is primarily going to be showing fractals, it's useful to know what a fractal is. But they are quite a complicated thing, and if we look here on Wikipedia at the formal definition of the Mandelbrot set, it is defined as the Mandelbrot set is the set of values of C in the complex plane for which the orbit of 0 under iteration of the quadratic map Zn plus 1 equals Zn squared plus C remains bounded. Indeed. We've not dealt with complex numbers on the channel before, and I've no intention of starting now. But we can take a rather simplistic look at it. The complex plane really consists of 2 axes, the real axis and the imaginary axis, and we can completely consider that x and y. And the objective is that for every point on that plane, we repeat a calculation until that calculation satisfies some constraint. And when we visualize the Mandelbrot, what we are actually visualizing is the number of iterations it took before that constraint became satisfied. This means we can start to reason about how to draw these things. We know we've got a screen, and in this case, because I really want to test the processing capabilities of my computer, I'm actually using a high-definition Pixel game engine application. I've got 1280 pixels across and 720 pixels down. The screen is of course in pixel space or screen space, but I want the boundary of the screen to be represented in the fractal space. And so at all times, my screen is actually going to reflect a small window in the entire domain of the complex plane, or the 2D plane that represents our fractal. And just for illustrative purposes, we can assume Up here, for example, I've got 0, 0, and down here I might have something like 2, 4. So what I'm actually drawing in the background is in a world space, and we've frequently done screen space to world space transitions before on the channel. And in fact, if you do want to look into that, you can look at my panning and zooming video, because I'm using code from that video in order to implement, well, the panning and zooming. As we move around the world, we effectively change these coordinates. So we could end up in a situation where the entire distance across the screen is really, say, 0.7 in our domain of the fractal, and going down might be something like 0.5. So for every pixel in my screen space, I can work out the position in world space by taking this distance and dividing it by the number of pixels. Therefore, I can create a mapping that will give me any pixel in my screen space and give me the precise floating point coordinate in world space. And what we will do then is calculate what's necessary to tell us what the fractal looks like at that coordinate. One of the problems we'll encounter with fractals is as we're zooming in, these numbers get smaller and smaller. In fact, it's not uncommon to start seeing numbers like this, because fractals can just keep on going in certain regions. Eventually, we're going to run out of floating point precision, and I demonstrated that in the introduction when everything fell apart. There are, of course, techniques to try and remove this limit of precision, but we're not going to be looking at that today. So all of my floating point calculations are going to be C++ doubles, which are 64-bit, to try and give us the most conventional precision we can get. The Wikipedia article goes on to detail some pseudocode for what is called the escape time algorithm for plotting a fractal, where for every pixel on the screen, we do the following calculation. And what we can see fundamentally is there is a calculation that contains a loop with an iteration counter. And as I said before, we're going to be visualizing the number of counts that there are before this condition becomes true. And internally in that loop, the maths is actually very simple, and I guess this is what is so wonderful about fractals and why people enjoy them, is how can such simplicity deliver such complexity. But that's definitely the topic for a different channel. I think the point I'm trying to make is it doesn't really matter if you understand fractals or not. What's important is it's a problem to solve, and it's a computationally tricky problem to solve. And we're going to look at developing this application from various different processing techniques to try and solve it more effectively. So this is a skeleton pixel game engine application. Well, not quite a skeleton, it's actually fleshed out with a fair few things already. And you can see I'm creating it at 1280 by 720 with a 1:1 screen ratio. This means it will be quite a nice high definition application, and it also means we've got a lot of pixels to process. And we'll just have a quick look at what the code is doing. In onUserCreate, I'm allocating some memory that's going to store the count of the iterations per pixel. So this array is the same size as the screen. But the action happens in onUserUpdate. The first thing I'm going to do is get the location of the mouse, and then I'm going to implement precisely the same code I used in the pan and zoom video that will convert the mouse location into the world location, and handle zooming with the mouse wheel or the Q and A keys. Once I've got my transformation from screen to world, I can work out where I am in the fractals space. And I do that by taking the top left pixel and the bottom right pixel, which of course is 0, 0 and screen width and screen height, and I use the screen to world function, again from the pan and zoom video, to translate that into this world coordinate system, so somewhere in fractal space. I've then got a little bit of user input, so I'm going to use the numeric keys to switch between processing methods, and the up and down arrow keys will change the number of iterations we're going to calculate. And here is the first important part. Instead of using frames per second as a performance metric, I'm actually just going to time with a high resolution counter how long it takes to call this function, create fractal basic, to which I give the pixels in the top left, the pixel at the bottom right, the fractals world top left coordinate and the fractal world bottom right coordinate, and the number of iterations. So we'll have quite a few of these functions, all with the same set of arguments. It's basically saying, please generate the fractal for this region. Once the fractal generation has completed for that frame, I then need to draw it to the screen, because so far all I've got is a 2D array of integers, which are counts, the number of iterations that that particular pixel required to satisfy that constraint. So I'm going to have a pair of nested for loops that iterate through every single pixel, and I'm going to colorize those pixels. And a big shout out to Ericsson, because what he doesn't know about fractals simply isn't worth knowing. He provided me with this little colorization function, which can take the number that's taken from the fractal array and, using some magic maths, converts it into a nice colour. And that's how we got these nice smooth transitions as we were zooming through the fractal at the beginning. So thank you, Ericsson. Once we've drawn the fractal, I'm then going to render some information about how long it took and how many iterations, and the rest of the class just contains these world-to-screen and screen-to-world functions, which handles the panning and zooming. There are two reasons I'm not using frames per second as a performance metric. Firstly, I'm uninterested in how well the Pixel game engine is performing in this task. I really just want to time how long it takes to generate that array of iterations to tell me what the fractal looks like. But secondly, and this is a trap for new players, frames per second can be a little bit misleading and may lead you to try and optimize your programs in an incorrect way. We know that frequency is related to 1 over the period, or time, the duration of the frame. And so if we plot this frequency, or let's consider it frames per second, versus time, we get a relationship like this. Up here, let's say we've got a really high frame rate, 500, and we make a change to our algorithm and notice that it drops to 400 frames per second. Naturally, we can calculate the time difference here simply by looking at the two values, and that was for a drop of 100 frames per second. So let's assume we have 200 frames per second dropping to 100. Well, again, we've only dropped 100 frames per second, but the algorithm is taking much longer. And this is why it can be a little bit deceptive to consider frame rate as a metric of performance. It is accurate, but it's not very intuitive to think of it in this way. Dropping 100 frames per second from 200 frames per second is not the same as dropping 100 frames per second from 500 frames per second. And this is why I prefer to just simply take frequency out of the equation and measure time. Because if something takes twice as long as something else, it takes twice as long as something else. There's no other way to interpret it. So here I use the rather wordy chrono library to give me 2 time points using a fairly high performance clock. And the only thing I've got going on between those 2 time points is the generation of my fractal. So let's take a look at this function. And this is my first pass, most basic, naive implementation of the Mandelbrot Fractal. Create fractal basic. Now, to all of these functions, I'm passing in the rectangular region of pixels, which in this case is going to be the full screen. And then I'm passing in what region does that correspond to in the sort of numerical fractal domain. And then I'm telling it what's the maximum number of iterations you can go up to, because I do actually want it to finish. I don't want it to just keep computing forever and ever and ever. I can work out the scaling factor based on the number of pixels, as I mentioned in the slides at the start, and then I just simply iterate through every single pixel in the required range. And I'm going to be using the standard complex number format, because we're working with complex numbers, to implement the Mandelbrot calculation. I initialize one of the values based upon its location in the 2D space, and I initialize the other value to 0. And then I sit in a rather tight loop, modifying this z value until the absolute value of z is less than 2, or I've gone beyond the number of iterations I've allowed for this calculation. Either way, eventually this loop will stop, and I can store the number of iterations in my big fractal array. This is basically a direct implementation of the pseudocode provided on the wiki page. The only difference being is I've used this inbuilt complex number type provided by the standard template library. So let's take a look. Right, well, that actually took quite a while to start, so I'll just use the middle mouse to pan over the fractal, and oh dear, as you can see, it's very slow. It's taking about 2.4 seconds. In this case, now we've got more information going on here, it's taking almost 5 seconds to update the frame. Time for the first stage of optimization, and some of you may laugh because you've probably noticed what the problem is, but have you actually compiled your program to run in release mode and not debug mode? A lot of new people, particularly those just coming to Visual Studio, will click that play button and not realise that by default it's actually going to run it in a specialised debugging mode, which is a lot slower than the release code you would give out to customers or end users of your software. So let's see what difference that makes. On Linux systems it's not quite the same, but you can specify a compiler flag to achieve the same result. So now we're building in release mode, 64-bit release mode in this case. Let's see what happens now. Okay, that's a lot more sensible. We've got a degree of real-time control over what's happening. We can see that given this particular set of equations to solve, it's taking about 1/4 of a second to generate the 1280 by 720 pixel image, and it's allowed up to 64 iterations maximum per pixel. So I can zoom in with the scroll wheel, and we can see the time doesn't change with the zoom, but eventually we just sort of run out of things. The fractal seems to just stop. That means we need more iterations if we want to keep on zooming. So I can press the up key and give it another 64 iterations of calculation. This has of course significantly affected our time. It's now taking about half a second per frame. And again, our fractal has stopped prematurely, so really we want 192, let's just keep going, 256 iterations, 320, it's grinding to a halt now, so we're almost about 1 second per frame, which does start to make things a little bit unusable. However, what we can see is we are rendering a Mandelbrot, and it, to all intents and purposes, and to my fairly ignorant eyes, looks okay. So for now we can assume it's taking about 1 second to do 320 iterations, and if we look at this little graph over here on the right, it's fully saturated one of my CPU cores. Now I have a 4-core processor and that has another 4 virtual cores, so there's 8 cores available and I've completely filled one of them. But before we worry about parallelism, are there any optimizations we can make already? Well, if you take a naive look at the code, and perhaps you're just starting out, you've not built up any experience yet, there are certain things you might think will help you out. For example, for every single pixel, we're calculating this multiplication, and we're doing one down here, and these are pretty much always going to be the same. So are there things that we can pre-calculate to take out of this tight loop? We're also doing other things like initializing this x variable every single time. So let's create a second function where we can explore pre-calculating as much as we can. The scaling side of things hasn't changed. And I'm going to stick with my loops, but I'm going to try and declare everything before we enter the loops. Perhaps that'll make a difference. So here are my variable types, and here are my 2 loops. Looking at what's going on with this calculation here, there is a linear relationship between the pixel position and the value that I'm constructing this complex number with. In that case, instead of calculating it each time, I can perform a running accumulation as we iterate across a particular row or a particular column. So I'm going to store 2 additional variables which represent the start of my fractal's rectangular region in space. And I know that the value of my x and y scale variables is the equivalent of how much fractal space do we change if we move in 1 pixel in 1 axis. So as I iterate across the screen in the x direction, I can simply accumulate the x scale value to give me the equivalent x position in the fractal space. And I can do the same outside in my y loop. I must remember though that as I'm iterating through y's, I need to reset my x's. This means in the loop I can now initialize my variables directly. There's no calculation required. So we have reduced this repeated calculation for every single pixel into simply an addition. There isn't a great deal I can do to change the nature of the fractal calculation just yet, so that remains the same. But we do need to store the result, the number of iterations for that particular location. In the original, this is where we were doing that, and we can see we've got another multiply in there. Perhaps we can pre-scale so we don't have to do that calculation every pixel. I'll add in 2 more variables, pre-calculated. One is called y offset, and one is the size of a row in pixels, because every time I move along an entire row on the screen, I effectively move down 1 in the y-axis. Therefore, for each y iteration in my loop, I'll increment my y offset, and this means I can simply store the number of iterations in my fractal array, now using a simple addition. I'll now quickly add in the code into our framework to call this function instead. So let's take a look. So here I have the original method before. I'm just moving the Mandelbrot in so it's actually got things to calculate. And for 64 iterations using the naive approach, it's taking about 0.25 seconds, maybe a little bit less. Okay, so I'll press the 2 button and we'll move to our new pre-calculated method, and it's taking, well, about 0.25 seconds, or a little less, i.e. we've really not achieved anything at all by doing this. Well, that's quite disappointing, but it's not entirely unexpected. I naively assumed I could do a better job than the compiler at trying to optimize the code. And indeed, I couldn't. The code performs pretty much the same. It probably is marginally a little bit quicker because the way that we're doing things is slightly different, but it's barely measurable. It's no good. And indeed, if anything, all we have successfully achieved is making the code more difficult to understand. So there's a little lesson to be learned here. Don't try and outwit the compiler unless you really know what you're doing. We've gone from reasonably simple code where it's quite easy to see what it's doing, we've got a loop with some calculation going in, into something, well, it's a lot more fragmented and nowhere near as intuitive to understand what's going on. I know what the problem is. It's that stupid standard template library. It's rubbish, isn't it? Everybody says it's really slow and bad. So I'll get rid of this standard complex and do it myself. Yes, that's got to be it. Nobody likes the standard template library. That must be the source of all my problems. So let's create another function and we'll hand code the mathematics this time. I'll call this function create fractal no complex. And again, exactly the same arguments. Even though this code was a little trickier to read, it probably did actually buy us a slight optimization. If nothing else, it got rid of some unnecessary multiplies. So I'm going to keep a similar structure. And I'll start by simply copying the code we've got already. It's my intention to remove the standard complex component. To do that would require you know a little bit about what a complex number is. But fortunately, all we're doing with the complex numbers here that is slightly strange is working out the absolute value and squaring them, and we'll look at that in a minute. But for now, I'm going to replace that simply with direct double values that represent the real and the imaginary components of the variables we had before. Inside the loop, I'm going to replace this line with this exploded maths. Complex numbers have their own set of rules for doing certain operations. I can assure you I'm doing nothing particularly fancy here other than implementing those rules directly. What was z is now z real and z imaginary. But we also need to change the nature of our condition. If we wanted to work out the magnitude of our complex number, we normally call the ABS function. But I can replace that with the following. Now all that's left to change is our initializations. So how have we managed to go from absolute of z is less than 2 to this calculation is less than 4? For all intents and purposes, we can consider a complex number to be a 2D vector. It has an x component and a y component. And when we think of it as a vector, it's far less scary, because we know if we wanted the length of the vector, its magnitude, we know that the magnitude of a vector is the square root of x squared plus y squared. It's Pythagoras. The constraint in our fractals while loop is fundamentally checking to see if the magnitude of the complex number is less than a certain value. In effect, I'm looking to see if the following is true. Well, given that we know that x squared plus y squared must always result in a positive number, I've absolutely no need to do this square root at all if I square the other side of the equality. Therefore, I can quite happily check for the occurrence of x squared plus y squared is less than 4. This is a nice optimization. We've removed the potential to have a square root calculation. Everything else in my create fractal no complex function is the same as before, so I'll add that into the program. So let's take a look. And it's starting with the naive method. I'll just bring that back in to give us some more data, and it's taking about 0.21 of a second. And if I press the 3 key, we'll bring in our no complex implementation. And great! Oh, we must be so much better than the standard library. We've halved the time required. Perfect. So that means, in theory, we can do twice as many iterations now and maintain the same level of performance that we started with. Well, as much as I'd love to be able to lay claim to being a better programmer than the countless number of experts that have provided the standard library, unfortunately I can't. I don't believe actually taking out standard complex components has optimized this code, and I'll show you why. It is very tempting to suddenly think that you're a much better programmer than the rest of the world. But in reality, we've not changed anything here at all. The standard complex operators will simply resolve to what we've already got, so there's no real gain there. The compiler is smart enough to do that. The one thing we changed was the nature of this condition. We've changed it to 2 multiplies, an addition, and a comparison. And if we look in the original implementation, actually what we were looking for was the absolute value of z being less than 2. For our needs, conceptually, we have optimized that function. However, what we have done is sacrifice the generic ability of the absolute function to do its thing, and that's what the standard library is pretty good at. This function will guarantee that it provides us with a sufficient level of detail and precisely the right solution in all situations. Our method doesn't do that. It simply gets the result directly what we need in order to satisfy the fractal calculation. And we can test for this by using the peak code function in Visual Studio. If we actually have a look at the definition of what is the absolute function, it calls the hypot function. And if we have a look at that, and have a look at that again once we get through all of these different layers, fundamentally it calls the hypot function. It's quite useful to look at the standard hypot function. It's part of C Math, and this is implemented by the C standard, and of course right now I'm using the Microsoft Visual Studio compiler and whatever implementation it's going to be using for that function. I can't readily access that, but what I can do is look at how the GNU implementation works. And this is suddenly very revealing. Whereas we had a pair of multiplies and an addition, the actual hypot function is considerably more sophisticated, with all sorts of checks, and still has the potential for a square root as well. There is a reason experts tend to write these functions, and there is a very good reason you should use them at all times. But occasionally it is useful to know if you can get away with some specific reinterpretation of the data you are using, you can actually gain some processing performance. But in turn, we have sacrificed the flexibility of the functions we want. So in effect, so far, all we have done is get rid of the square root in this tight loop, and we've doubled our performance. So it seems to have been quite a lot of effort to get to a rather unsatisfying conclusion. I think it's time to bring out the big toys to play with, and we're going to look at the extensions provided by most modern day processors that allow us to manipulate numbers in parallel. And I don't mean threads just yet. So far we have been using the fairly bog standard arithmetic logic unit component of our processor. This allows us to provide 2 numbers, an operation, and it spits out a result. And we've been asking it to do that as fast as it possibly can. Whilst we're developing the fractal, what you may have noticed is right now there's no need for data to communicate back with any memory. We simply read from memory, perform a computation upon it, and then ultimately write that result back to the memory. And as we're generating the fractal, we're doing that 1 pixel at a time, all the way along, down, and then all the way along again. Games developers have pushed CPU manufacturers for the last 30, almost 40 years now, to develop better and faster hardware. And one of those things happens to be called a vector processor. And these have existed in various forms over the last 20 to 30 years. We used to have what was called the SIMD streaming extension set, or I probably got the order of that the wrong way around, and these days we have something called AVX. And specifically for this video I'm going to be looking at AVX 256. And these are quite useful because they're very flexible and they allow us to implement quite fine-grained parallelism into our program without a great deal of effort. Let me explain why it's a bit different. They are literally a processor extension, and so conceptually what I'm going to draw here is an extension to our ALU. And what I want us to imagine is that instead of just having the one ALU now, we have 4 of them. And each one of these ALUs can take in a pair of doubles. And each one of them can spit out a result. But they all perform exactly the same operation. So if the operation is an add, all the ALUs will perform an addition. Specifically, the vector extension sets work with memory of a specific size. I'm going to be using AVX2, or I call it AVX256, because that means it has a single register which is 256 bits long. So start with naively bit 0 over here and bit 256 somewhere over here. One of the nice features provided by this ecosystem is I can use these bits partitioned in various ways. I want to process doubles, and my doubles are 64 bits each. So I know I can fit 4 doubles into a single register for this extension. 64, 128 bits, 192, 256. I could, however, work with less precision and work with 32-bit floats, which means I can operate on 8 numbers simultaneously, all with the same operation, but fundamentally all with unique data. And in fact, you can go even further. If you're working with integers and you have a 16-bit integer type, then naturally you can start fitting more of those into this vector processor. And this vector processor follows what is known as SIMD, single instruction, multiple data. Regardless of how we've partitioned up the vector, the individual datas inside the vector remain distinct, but they all have to operate with a single instruction. So single instruction, multiple data. If I now implement our fractal routine using AVX2 or AVX256, I'll be able to process 4 64-bit doubles simultaneously. I'll also be able to take advantage of some bonus functions you get as part of this extension. There are instructions, for example, that allow me to multiply and accumulate at the same time. And all of these instructions are guaranteed to happen fairly quickly in silicon. They could in many cases be far faster than the standard ALU way of doing things. So it's probably a good idea when we're working with large data like this, but with simple instructions, to think about using the vector coprocessors on your CPU. To start using such weird and wonderful components of your processor, you need to include the right library. And for C++, it's the Intrinsics library, because I'm not going to be writing this directly in assembly. Fortunately, this library provides some convenient C and C++ wrappers for the individual functions, so they do actually compile down to the most minimal assembly you need, but remain quite convenient to use for regular C++ programming. So I'm going to add in yet another function. Create fractal intrinsics. And as before, it's got a similar startup. And I'm going to simply cut and paste in the intrinsic equivalent of the fractal generation algorithm. Kaboom. Yes. This is one of those rare occasions where I'm just going to ask you to take my word for it. I don't really want to go into detail in this video about what's going on here. If you are interested in how I've gone from converting the very simple fractal routine into using these intrinsics, do shout out in the comments below and I'll make a video specifically about that conversion process. But what I want you to take from this is that it does work, it's converted over to intrinsics, and I am indeed going to be operating on 4 pixels simultaneously with each instruction. So yes, I've no plans on detailing precisely what's going on here, but if you are curious and do look at the code, what happens is our 256-bit registers are specified as being comprised of 4 doubles, all in parallel. And so all of the calculations to those doubles happen in parallel too. In this instruction, I'm multiplying 4 xpos offsets by 4 x scales and storing the result back in xpos offsets. You can think of it each time as working with a little array of 4. Although things start to get tricky, and that's why it needs to be a specific video rather than going into the detail, is you can't implement if. So the condition that our fractal stops on is significantly more complicated now, requiring a little bit of binary mathematics in order to implement. You can see the loop is actually here using this goto and repeat label. And once it's finished looping, we'll unpack the 4 values in our special 256-bit register into the fractal array at 4 adjacent locations. But like I say, worthy of its own video if there is enough interest, and if you are interested, do shout out in the comments below. So time to add in that method. So let's take a look. Here is our naive approach again. Again, bring it to the middle, 64 iterations, about 0.25 of a second. If I now compare that to using the AVX instruction set, suddenly we're now an order of magnitude better. So this has been a real performance change. In fact, you should always try and measure performance in orders of magnitude. So this gives us the real ability now to start navigating the fractal. And we can see we've very quickly run out of iterations, so I'll ask it to compute some more. And it can happily do that without sacrificing too much performance. So this is very nice. As we start to zoom in and the demands become more, let's add in a few more iterations, we do see that it takes a bit longer each time. I've changed this now to 1024 iterations, and we're looking at updating the entire image in about 150 milliseconds. In fact, at this level it's quite possible to start reaching the end of our floating point precision. But as we zoom in and things require more and more iterations, we do start to slow down. So now we're at about a quarter of a second. So this is originally the time of our naive method to do 64 iterations. Let's go back to our naive method and see how it compares. So I'm just waiting for it to do the computing, and now it takes about 1.9 seconds to actually update the screen. In fact, 2 seconds in that instance. So that's 1024 iterations. And if I go back to our AVX implementation, yeah, a good order of magnitude better. So it's still quite usable for exploring the Mandelbrot fractal. And you'll see we're still only using 1 CPU's worth. So that's actually quite a good improvement. But I do have more than 1 CPU core. So let's have a look at using now our very fast vector extension implementation, but in multiple threads. Naively, this is quite an easy thing to implement now using some of the more modern C++ features. Threading has always been quite tricky, but the newer features, and I say newer, I really mean sort of as of C++ 11, they do actually make your life a bit easier in this instance. And so I'll add another function called create fractal threads. At the moment, we're trying to process the full screen using a single thread. Threads allow us to do things in parallel, and they'll occupy more and more CPU cores in order to do that. One of the advantages we have working for us here in Fractals is that we never need our threads to actually communicate any information with each other, nor do they interfere with each other's memory. So in reality, working with fractals and threads is quite trivial. I'm going to take my entire screen and then partition it into the number of threads I want to test. I'm going to partition it in columns. So if I had 4 threads working for me, I would have thread 1, or thread 0 over here, working on this column, 1, 2, and 3. And they'll all go away and chew on their data, and they might not all finish at the same time, but I'll wait until they have all finished, and then I'll proceed. And that's going to be the bit that we time. Since we already have a function for calculating the region of a fractal, all I need to calculate is what is my subregion now that I'm going to allocate to the thread. And I'm going to add to the program a max threads value. We'll do that at the top. I'm going to specify 32 threads. Now you might think, oh, you can't have 32 threads if you've only 8 virtual cores. Well, I can, because my threads are not all going to finish at the same time. And we'll see why when it starts rendering. In my function, I'll create a small array of threads, and then for each subsection in my screen, I'm just going to create a thread calling our create fractal intrinsics function we created earlier. But the only thing I need to change are the arguments to that function. So we can specify it only computes a particular region of the fractal. It's kind of amazing how these things come together, isn't it? By virtue of creating the thread, it will also start to compute it. So I'll have a second loop which waits for all of the threads to finish. And that's it. We can now add this into the program. So let's take a look. And I'll start actually by going to our AVX2 implementation, so I can move things around a lot more smoothly than I could before. And I'll press the 5 key now to implement threads. And well, we've got a small performance increase. Go back to vectors, and this is threads, but it's not a huge one. I wonder why that could be. Let's zoom out a little bit and find somewhere else to look at. I think we might need to zoom in quite a bit. So let's add some more iterations. I'll stick it back on threads mode as well. That would help, wouldn't it? we'll give it 1024 iterations. I think that should now be our benchmark. So 1024 iterations, and I'll just quickly compare that with the vector method, 0.04 versus 0.02. So we've doubled our performance by moving to threads. Now, the reason it's not consistent is in this particular instance, for example, we've not really got much to do. A lot of our threads will just hit the end condition, whereas over here there might be a lot more to compute. And in fact, it's spatially dependent. We're partitioning our screen into vertical columns processed per thread. So some threads are definitely going to finish before others. And this means, depending on how busy one particular column is on the screen, will actually be the slowest part of our algorithm, and everything else will be dependent upon the complexity of that column. Let's keep zooming. I love fractals. You never get bored of this because you can always find something different or some interesting pattern. Maybe we're getting to the point adding more iterations worthwhile. I mean, we can still keep computing these iterations, but of course our while loop will exit at some point, so we might not actually always compute that many. That's one of the difficulties in benchmarking something like this. You really do actually need to understand what the fractal is doing and which regions are going to require more processing than others in order to do a fair comparison. But for our simple needs, this is good enough. In fact, we can now reach the limits of precision. And you might not be able to pick this up in the YouTube video, but you can on here certainly see vertical columns appearing in the fractal data. In fact, there'll be 32 of them, one per thread. And that's because we're getting to the point now where we have limited precision on our double values. And so some of them are duplicating, and there's a little bit of error that's propagating from one region to the next. Purely spatial error. Don't forget the threads do not communicate with each other. But there could be a duplication of computation. And so that precision is highlighting the boundaries of our threads. And of course we can go into sort of oblivion here and it just completely falls apart. Let's zoom all the way out because it's nice. I like watching these things. That's one of the reasons I've also mapped the Q and A keys to the zoom, because doing this with the mouse wheel makes your fingers a bit tired. Also interesting to look at how the performance changes over time. So you see how it's actually getting quicker when we're not quite as far into the fractal. And now, for some reason, it's got really, really slow. And that's because there's a large region of the fractal. It's doing all of this computation, but never hitting the constraint. So this is potentially our worst case scenario. We've got half the screen here on the left that's literally just maxing out. It's always hitting the maximum number of iterations. If I increase that number, you can see the color changes to tell us that it's hitting that maximum number of iterations, and the time taken is increasing. I'll just compare that with the vector method now. And the vector method, see, doesn't actually buy us anything at all. It's considerably slower than the threaded method. Let's go back. So the threads of vectors is working very well for us. We can even look at the CPU chart here and see the difference. If we go to a purely vector-based implementation, and this is really chewing through the numbers, because even though we don't see any detail here, it's had to calculate everything up to the maximum number of iterations we allow. Here with vectors, it's saturated the one core, but if I go over to threads, hold down the button, we've moved over to threads, it's now starting to occupy a lot more of my processor. This is good. We're getting value for money finally out of my CPU. There is something else worth noting here, and that's this little window at the bottom, and I apologize if the One Lone Coder logo obscures what I'm looking at, but it's here. We're constantly creating new threads, and those new threads are exiting, and this does have a performance overhead. Spawning a thread these days is a lot faster than it used to be, but there is still an overhead attached to it. So what I'm going to do next is create another function which uses a thread pool. A thread pool is a collection of threads that are already running. and they're just waiting to be started. They're literally itching, really trigger happy to get going computing some data. And they're very useful for just chewing through large amounts of data if you know all of the constraints in advance. So for my thread pool, I'm going to have an array of threads, and all of these threads are going to be stuck in a while loop, waiting to be given a trigger to start. This means the threads are always in existence. I don't need to request the operating system create a new thread handle for me and pass it over and give me the appropriate stack and do all of the things it needs to do when normally creating a thread and cleaning it up. Instead, I do it once at the start of my program, and I just tell it to wait until I need it to do something. We're going to remove all of that overhead. And so now I'm going to add our final implementation, and it is probably the most complex implementation, and again I won't go into too much detail regarding some of the thread handling mechanics that are going on. Create Fractal thread pool is going to be a bit different to all of the functions we've had so far. It needs some stuff set up in advance. And just to keep it distinct and so I don't contaminate the rest of the program, I'm going to create a structure called worker thread, which contains the parameters we've typically been specifying as arguments to the other functions up there. It also contains a handle to a thread and some pointers to the outside world. Again, not going into too much detail. When I want the thread to start, and I don't mean start as in OS start, to start actually crunching through the numbers of the fractal, I'm going to call the start function, which quite deliberately looks exactly like all of the other functions we've been using. Except this time it prepares the structure's local variables with the correct data and triggers a condition variable, and that's some multi-threading magic item which tells a thread to actually get going with something. Because the actual creation of the fractal data is going to be occurring in this thread function, and this is going to be happening all the time. This is the while loop I was telling you about in the slide. Our while loop effectively sits waiting for the condition variable to be told to start. Once it receives that command, it's then going to go and implement the intrinsic function. I've just copied it in verbatim here. This means before I can use any of the threads in my thread pool, I need to have an array of them, and I also need to have initialized some of the properties. So I'm going to use the same max threads variable I was using before, and I'm just going to iterate through that array of worker threads, set up some of their information, and start the threads. I'm going to call this initialize thread pool function in onUserCreate. Now, in the create fractal thread pool function, as before, I need to allocate a particular section to a particular thread in that pool. But instead of creating the thread explicitly, I just call the start function as part of my worker thread structure. But I now need to wait until all the threads have finished. And whereas before I would wait for the thread to literally expire and see when I can join with it again, I don't have that option now because my threads will never close down unless I explicitly kill them. And so to implement this, I'm going to add in a standard atomic integer, which is sort of a thread-safe variable called nWorkerComplete. Every time a worker thread has completed working on its part of the fractal, it's going to increment that variable. Therefore, in my function, if I set that value to 0 before starting the workload, and then I simply sit in a very tight while loop, waiting for that workload to complete. I mean, this loop literally does nothing other than waiting for that value to indicate that all of the threads have completed their work. No doubt there is a more elegant way to do this, but I'm just conscious of video length. And so for the last time to add that function to the rest of our program. Create fractal thread pool. Now I've also added some code just to clean up after myself. All those threads need shutting down and memory needs removing. That's all available in the link from the GitHub in the description below this video. But for the last time today, let's take a look at what's happening. So here we've got the naive method on the starting screen, not even going to move it, 64 iterations, about 0.05. I'll move straight to a vector extension, so that's 0.06. If I go to threads, well, threads is a little bit slower at the moment because the reasons we just discussed. If I go back to thread pools very fast, so about 1 millisecond per update using the thread pool approach. So let's throw some more iterations at it. We've been standing around 1024, I think is a good number, seems, for everywhere in the array. We'll compare that back to regular threads again. So regular threads now taking about 100 milliseconds, thread pool taking about 60 milliseconds. So we can zoom in and start exploring the fractal. See, at any point we can actually reduce the number of iterations and see what effect that has. So we can see it does require iterations as you are zooming in. We'll just keep going. It's a nice fast zoom. Now this is interesting because we have hit a limit here, so let's get that right back up. 1024 iterations. So I think with this application we can confidently explore a fractal to the maximum of the 64-bit precision of the double that we have available. And we can also explore these things at a pleasing enough frame rate. Drag around, let's go and have a look what's going on down here. So that just looks like a never-ending spiral. I'm sure YouTube is hating me for this. Tell you what, let's go and explore one of these arms because these look a bit different. See, look how fast it is now, zooming in everywhere. We'll just keep going, keep going. Yes, that was really nice. So it took no time at all for us to get to the point of oblivion. Oh, lots of repetitions of the Mandelbrot itself, of course. Fractals are great. I mean, I've been playing with this program all week and I've still not got bored of finding lots of interesting different shapes and phenomena. It's really nice just zooming around and playing around with it and trying to experiment with the colours as well. And again, a big thank you to Ericsson for providing with the colour code. In the GitHub, unusually for Windows, I'll upload the binary of this if you do want to play with it without compiling it yourself. Of course, just be careful, scan it, make sure it's right for you to be running some software which is unsigned, because I don't have a signature for these things. Now, this is interesting. This is probably the worst case scenario because most of the threads are doing the absolute maximum and there's just this one thread in the middle that's not having to go very far before it resolves to a particular colour. So it's in the program's interest perhaps not to break things up in columns. Maybe a grid approach would be better, but hey, these are all the different things we can keep experimenting with. That's the beauty of optimizing like this, is there is always something else you can do. And so that's that, a fairly whirlwind tour at trying to brute force process your way through a problem. Lots of detail has been overlooked in this instance, and we haven't looked at sort of the micro optimization things either. What if we did everything in assembly language to begin with? Could we actually outwit the compiler? Lots of interesting questions to try and answer. Anyway, if you've enjoyed this video, a big thumbs up please. Come and have a chat on the Discord. The source code and the binary for this is available from the link below in the description on the GitHub. And I guess stay safe during the lockdown, take care, and I'll see you next time.